Hi there, my name is Graeme MacGilchrist. I'm going to present my poster on chaos in ocean ventilation. Ventilation is the process by which water is moved from the surface ocean into the ocean interior, and there's a traditional perspective on ventilation, particularly in the subtropics, by which ventilation is controlled by the time mean gyre circulation. So water is ventilated or subducted in the northeastern corner of the gyre, and then it's thinking about the North Atlantic, and is then advected around by the gyre circulation down into the southwest. At the same time, the ocean is highly non-linear, and there's a prevalence of mesoscale eddies and non-linear features in the ocean, which will act to complicate the pathways along which the water will travel into the ocean interior. And the effect of this turbulent ocean on ventilation has not been fully quantified. So the impact of these mesoscale eddies and the turbulent aspects of the flow are to stretch and filament fluid parcels. And there's a box in the corner of the poster here explaining that process known as strain. And essentially this strain happens exponentially in time. So a coherent blob of fluid that moves down, that is ventilated into the ocean interior, will be rapidly stretched out and filamented. And we can quantify the impact of this in relation to the ventilation process by comparing the timescales over which a region of the ocean is ventilated versus the timescale over which it's strained, which can be defined from the large-scale properties of the flow. So that's what we've done in an ocean general circulation model, which is eddy permitting, so there's enough resolution in the model in order to resolve some of these non-linear features. And that's what this figure here, figure 3, shows. So in the top panel we have the ventilation age, which is worked out by tracking parcels of water or particles back to the surface and determining how old they were or how old they are. On the second panel, so this is the ventilation timescale, on the second panel we have the strain timescale, and the ratio of these timescales will tell us the expected, or gives us an order of magnitude estimate for how filamented a ventilated parcel of fluid in a particular region would be. So the reason that we can use that, or the reason that that matters, is that then the extent of filamentation in a particular region gives us an impression of the chaotic nature of the pathways by which particles have travelled to a particular region. So now in this is explained schematically in figure 4, where we look at, apologies about that, we look at essentially schematically looking at the pathways followed by particles from the ocean surface, from the mixed layer, down into the ocean interior. In the blue case, we're considering it to be a laminar flow, so where we have a small ratio, or the ratio of the ventilation timescale to the strain timescale is small, and so we have a small filamentation number, which is the ratio of the two. That one is in blue, where we have a small number, and therefore the filament width is large, and so all the particles will have come from the mixed layer at a roughly similar time and from similar locations. By contrast, if the flow is filamented, a large filamentation number, then the pathways by which the particles, adjacent particles on the density surface will have travelled will be chaotic, and they'll have come from all different areas at all different times. So just to bring it back to the original context of the argument, the chaotic nature of the particles, or the underpinning theory behind traditional views, is that the flow is predominantly laminar, and the blue case is what's happening, that the particles are moving, or the parcels of water are moving coherently into the ocean interior. But in reality, given the size of the large filamentation number, it's more likely that the pathways have been chaotic. And we evaluate this explicitly finally in this final panel, where we actually perform this mapping that is here in figure 4, and we can see the features, the chaotic nature, the small filaments created by mesoscale variability, and it shows the fact that a lot of these particles, a lot of the regions of the ocean, have been ventilated in a much more chaotic manner than the traditional paradigm. And that's just summarised here. So thank you very much for listening.